Glad you're here. Today's the 3rd. All right. And some areas here. Okay. Sorry, we would have already been started, but I could not find which slide we were on. I was just in the process of finding that when you came in. I did want to make a couple of minor announcements. I don't think it will affect this class any, but it might. I do have 2 office hours changes this week that I know about. Hopefully that will be all. First, tomorrow I have a doctor's appointment, okay? And I saw this early in spring break week, and I don't remember exactly what time it is. I think it's 11:20 or 11:40 is when my appointment is tomorrow morning, which means I'll be here first thing in the morning. But where it would impact you, I have an 8 o'clock class, so I'll meet for that. My 9:30 class, I haven't counted back to see whether we'll meet at all or whatever. But my office hours are normally 10:45 until 1:15. If it's 11:20, there's no way I'm going to be here at 10:45 because I have to be there. If it's 11:20, which I think is what the time is, that means I have to be at the labs at 10:20, which means I have to leave campus by 9:45 or something like that. So basically, my 9:30 class, I'll basically just have time to meet with them, and we'll talk about when we're going to make up the class, and then I have to leave. So I will not be in my office at 10:45. I should be back if the appointment is 11:20, which I think my wife said it was this morning. If that's the case, hopefully it'll be over by 12:20, which means I'll be back in the office hopefully by 1 o'clock. If not, I might be late for class. But basically, almost all my office hours tomorrow, from 10:45 to 1:15, except for the very end, will not be in my office. Okay. Then on Friday, I have an infusion. So it's scheduled for 8 o'clock in the morning. I have to be there by 7:45, so I won't be on Birmingham campus by 7:45, and I will be at the infusion all day long. So I won't be back on campus at all. So that's office hour changes this week. Have you seen or heard, I can't remember when Honors and Awards Day is. Oh, you have something on it? I think it's next week, not this week, but seems like it's around the 12th. That's right.
I was trying to see if it was in the pamphlet for graduation.
What is that?
That's what they gave us.
Oh, the graduation information. Oh, yeah. No, I doubt it. It would be because this is only talking about graduation. I think it's next Thursday, not this Thursday. If it's next Thursday, if it's this Thursday, that means that trig class is going to miss 2 days in a row. I hope that's not the case. I think it's the 12th, but I've got to go and check on that. But anyway, those are the only announcements I know for this week. All right. We did this slide last time, and we did the 2 examples after this slide last time. We're on page 177. This is Chapter 3, Differentiation. 3.9 is derivatives of general, exponential, and logarithmic functions. and we were at the middle of page 177, logarithmic differentiation. Okay? Now, it's not this slide, it's something that follows this slide. And here's what it is. Here's example 5. Sometimes if you've got really complicated problems such as this, let me get my pen color back to where it needs to be, a dark color. What if you had this as a function? F of x is equal to x plus 1 squared times 2x squared minus 3 divided by the square root of x squared plus 1. And it says, find the derivative of that thing. And frankly, I would look at that and come close to screaming, okay? Because this is a product rule up here with a exponential part here, sort of a chain rule part here. No, that's just a product rule thing. But then down here you have a quotient rule, and in the quotient you have a radical, which can be written as a power, but then it has a chain rule feature to it. I got, oh no, okay, what a mess to do that brute force. But now that we know about logarithms, we can do some things to help make this a little easier. What would happen if we took the log of both sides? The log of f of x would then be the log. Now I'm going to do a little bit of changing here while I'm doing it. I'm going to write the first one the same, x plus 1 squared times 2x squared minus 3 over, I'm going to write this one as x squared plus 1 to the 1/2. Okay. Just because I don't like to write them in radical form, okay? I like to get it in exponential form. Okay. Now, the next thing we do is use our rules for logarithms. I don't know if you remember these, but this is one place where logarithms really help out a lot, okay? And here's what it is. Do you remember the rules for logarithms? Just in case you don't, I'm trying to remember if the, yeah, back in algebra at the very top of they have the laws for exponents, but I don't see the logs for logarithms. Yeah, boo hiss, okay? But they come right from the same source. Yuck, I thought they were in here. Let me see if they happen to be in the back. I don't think they are, but let me just check and see. Ah! Yes, they're in the back part. You got integration at the very end, differentiation right before that, and then you have a page that says exponential and logarithmic functions. And here's what I'm getting at. You see that third column there? It doesn't have a page number. It's the page before differentiation. Top of the page, the third column. The log, and it can be any log, we're doing the ln log, of a product is the sum of the logs, right? The log of a quotient is the difference of the logs, right? And the log of a power is the power times the log. You see it? Okay. We're going to use every one of those on this problem. First, we have the log of, I guess I'll take this very slowly, okay? The log of x plus 1 squared, right? Plus, because that's a product, the log of 2x squared minus 3 minus, don't have enough room because this is a quotient, the log of x squared plus 1 to the 1/2 power. You buy that? The product and a quotient, the product is the sum and the quotient is the difference. Okay? But we have a couple of exponents here. So this is also 2 times the log of x plus 1 plus the log of 2x squared minus 3. There's not much we can do with that one. Minus 1/2 the log of x squared plus 1. All right. This is the simplest form we can do it. Okay? Now what we're going to do now is differentiate this. Okay? Now, if you'll turn back just a little bit, the derivative at the bottom of page 176, derivative of a log of a function is the derivative of that function divided by the function, right? You see it? In fact, here it is right here. Okay, here it is. Derivative of a log of a function is the derivative of the function divided by the function itself. Right there. And that's what we're going to be doing here, taking the derivative of this. So basically, the derivative of this, d by dx of this, right, is going to be f prime of x. That's what we're looking for, okay, divided by f of x. But we know what f of x is. It's that thing, okay? We'll get back to that in a minute. Well, if we took derivative of the left-hand side and you got that, let's take the derivative of the right-hand side. And what do we have here? Going to here, d by dx of this thing, okay? Well, that's going to be 2 over x plus 1, because the derivative of the log is 1 over the thing, right? Okay? Plus, and derivative of that function is going to be, go back to this thing, that's going to be the derivative of the function, which is 4x, right? Derivative of this thing is 4x. You see it? Over 2x squared minus 3. The function itself, right? Okay? Minus 1/2. Derivative of this thing is 2x, right? Over x squared plus 1. Right? Okay. The 2's out front, and the log of this is its derivative, which is 1 over itself. Okay? Plus, derivative of this is 4x over itself, 2x squared minus 3. Minus 1/2, derivative of this, which is 2x, over itself, which is that. Okay? So now we've got derivative. All we've got to do is plug in what f of x is, but actually multiply it by the other side. So really what your f prime of x is, then this thing, 2 over x plus 1 plus 4x over 2x squared minus 3 minus 1/2 2x over x squared plus 1. All that times what you started with. X plus 1
squared times 2x squared minus 3 divided by, and you could either write it as a square root or you can write it as a radical. An exponential function. I would just as soon write it as an exponential function, but since they wrote it as a radical, we write it as a radical, the square root of x squared plus 1. There's your answer, okay? A lot easier than trying to do 2 product rules, 1 quotient rule, and at least 2 chain rules, okay? All mixed up together. That's what we get. Let's see how close we are to their answer, okay? Finally, at the bottom, 2 of x plus 1 plus 4x over 2x squared minus 3 minus, dumb. This 2 and that 2 cancels out. So it's just minus. Say again? Yeah. Okay. That makes it a lot simpler looking, doesn't it? Because I'll do it up here. That cancels that. Okay. So it's minus x over x squared plus 1 times that original function. X, and that's a really ugly plus sign. Let me clean that up a little bit. I can hardly read. There it is. Okay. Times x plus 1 squared times 2x squared minus 3 divided by the square root of x squared plus 1. See how it works? Boy, isn't this a handy little thing to know and remember. Especially when you combine it with the properties of logarithms. Now, I don't know who you had your pre-calculus algebra under. I know usually when I teach it, we just barely get to logarithms, and sometimes we don't emphasize the properties well enough. This is where those properties come into play really, really well. Okay. Any questions on example 5? Okay. I think we're ready to go to example 6. And I believe the this is a graph of what we're going to do in example 6. It says differentiate for x greater than 0, a. And the a one here is f of x is equal to x to the x. What? Okay. We know how to differentiate x to a number, x squared, x cubed, x to the 15th, x to the minus 1/2, x to any power. We know how to do that. That's just a power rule. We also know how to do f of x equals some base to the x. That's the exponential rule. But now we've got them combined together. X to the x, we got x as the base and x as the exponent. How in the world do we do that? Same trick we just used. Take a log of both sides. This gives you the log, sorry, I got the hiccups. Log of f of x, and that's going to be the log of x to the x. Sorry. That makes it look like we've just made it more difficult, right? But first thing we're going to do, what the ask is to differentiate it. So, sorry. Let's differentiate it, okay? And like we just did, d by dx of this thing, and we're going to be d by dx of this thing. Sorry. Just like we had before. What's that? No, I've got hiccups. And I can't stop. So maybe I ought to run and get a long. long swig of water and see if that would help. I kept thinking they'd go away, but so far they're not. But you remember before, what was the derivative of log of a function? It's the derivative of the function over the function, right? Just like we did before. And this, by the way, is what we're looking for, f prime. That's what we're looking for. But before we take the derivative of this, in fact, I'm going to postpone taking the derivative for now, and I'm going to rewrite this as, remember the rule for logarithms? Logarithm of a power is the power times a logarithm. Sorry. X log x. Huh? Okay. Let me pause this just a minute. I'm so sorry. Now. All right. This is the thing we're going to do the d by dx of. Okay? Because if we had done the d by dx of log x to the x, we would have done that to begin with. Well, not quite. Okay, what is the derivative then of this thing? Well, that is a simple product rule. Can't get out of that, so what would that be? Say again? Okay, I can't hear one. Okay. Yeah, the first part would be the natural log of x. Derivative of the first times the second, natural log of x, plus x times the derivative of natural log of x. And what's the derivative of the natural log? 1 over. So that would be plus x over x. Well, x over x is 1. So that's what its derivative is. Okay? Okay, seems like I sealed, whoa, my eraser didn't pick up. Okay, here we go. All right. So what we did, you did it right the first time. Derivative of the first, 1 times log x, that's it, plus x times d by dx of log x. And if you go back and see what derivative of log x is, on Theorem 2, page 176, d by dx of log x is 1 over x. Okay, so this is log x, that first one you did, plus x times 1 over x, I can't write, and x times 1 over x is just 1. Okay, so that gives you log x plus 1. Okay, now all we do is multiply your f prime of x is now log x plus 1 times your f of x, which is x to the x. Okay. Now, they graphed it for you. Thank you very much. But if you have a graphing calculator, you can graph it as well. I sure would hate to have to pick this out, but this is only good for x greater than 1. And the reason for that, you don't ever want to put a negative number as a base for any power whatsoever, because it's going to flip-flop back and forth. It's not defined, okay? And then especially if you do this, log x, log x is not defined for x less than 0 or even equal to 0. So our x's here are all greater than 0, okay? Not even 0, okay? But anything to the 0th power is 1. So this does appear to start at 1, even though it's not defined at 0, okay? And then if you raise, say, 0.1 to the 0.1 power, okay, that's going to be, you know, for a little bit, that's going to be a decreasing function. But not really for very long, and after a while it starts increasing and increasing really fast because your base is getting bigger and your exponent is getting bigger at the same time, so that goes up pretty quickly. Now, so that's that. What we've just done is the derivative of this would be the slope at any point along here, and of course that's going to be equal to 0. This is never equal to 0. This is equal to 0 where log x is equal to minus 1, okay? And where log x is equal to minus 1, it would be 1 over e. And e is about 2.7 something or another, so that's close to 1/3. So if you think this is 1, 1/3 is about here, yeah, that's really close to 1/3 is where that's equal to 0. So it's decreasing to there and then increases forever after that, okay? Because the derivative, this is always positive, and this is positive anywhere after log x equal to minus 1, log x equal minus 1, like I said, at 1 over e. So anywhere past that, you're in the increasing function. Okay. So that was the A part. Let's look at the B part. Now, this is 6b. Take the, or differentiate, and again, x has to be greater than 0, not even equal to 0, greater than 0. G of x is equal to x to the sine x. X raised to the sine x power. Oh boy, what a pain in the neck that looks like. Okay? Guess what trick we'll use? Take the logs again. Okay? This will be log of g of x is equal to the log, natural log of x to the sine x. Okay? Which will be, take your exponent out in front, sine x times log of x, right? Now we differentiate both sides. What's the derivative of log of g of x? G prime of x, which is what we're looking for, over g of x, which is what we know. And that's equal to, and here we'll take derivative, don't worry about this one, take derivative of that one. Again, we've got a product rule, right? What's the derivative of that product? This one here. A little louder. Okay, it's derivative of sine times log of x. What's the derivative of sine? Cosine. So that'll be cosine x times the log of x, okay, plus sine of x times the derivative of log of x, which is 1 over x, right? So the first one is derivative of the first times the second. Derivative of sine is cosine times the second log x, plus the first, sine x, times the derivative of the log x, which is 1 over x. Okay. That then, your g prime of x is then going to be this thing, which is awkward in itself, cosine x log x plus sine x over x. That's a really ugly sine x. My pen slowed down and I couldn't tell where it had written, and I guessed poorly, times what g of x was, which is x to the sine x. Okay. I forgot to check and see what the answer to the first one was. 1 plus log x, I said log x plus 1, doesn't matter, times x to the x. And the second part is sine x over x plus cosine x times log x. And I guess we should put something in parentheses there, maybe all that in parentheses. Okay, I don't know. Okay. Times sine times x to the log x. Got it. Now, I sure didn't want to graph this one, so I'll let you take a look at it. When x is equal to 0, of course, x can't be 0. Remember, it can't be. But if it were equal to 0, sine of 0 is 0. So this is almost 0 to the 0, which is anything to the 0th power is usually 1. So it is starting awfully close to 1, though it's not defined at 1, at x equals 0. So it started there, and again, dips a little bit. Dips a little bit and has a horizontal tangent there. Then goes up and has another horizontal tangent. Goes down and has a long horizontal tangent. Goes up and has a real quick horizontal tangent. And then again another long one. And it keeps this going. And if you think about it, nose is itching like crazy. I don't know if it has anything to do with the hiccups or not. Sine x is 0 when x is any multiple of pi, right? 0, pi, 1, pi, 2, pi, 3 pi. Those are all zeros there. Okay? Now, so x to the 0 power, anything past 0, it should be 1 then. So it's 1 then at, see if there's 2 and here's 1. That would be I see the 3.14. That would be about here. But we had another 0 in here we didn't pick up. And then 2 pi would be 6.28. There was that one bit. 3 pi would be over here, which would be 9 point something. So you see your those are right regular there. I just don't see the one that's here. Why have we missed that? It's because some other combination of x's and sine x leads to 1. Not to worry about that too much. Okay. The x sine x, notice, is never 0. It gets close to it, but never becomes 0. And by the way, where you have the downturns here, we didn't have one quick downturn here, which you've got almost the same thing there. But this is constantly going up. This one has a little downturn here, then one here, and then one here, and then it's going to have another and another. Well, that's where your signs go negative. So the sign is negative anywhere between your
even pies, and the next half pi. Sorry. So here it's negative here. It never reaches 0, and negative again there. Okay, that's what gets the humps in there. And I guess that's all we need to say about it. It's a real bear of a function, and who messes with that anyway? I don't know. But you can still take its derivative. Now, the next section here deals with hyperbolic sines and cosines. Now, I think I've mentioned this before in class. Your field of study is going to be radiology or something like that, is it? Or say again? Biomedical science. Okay. Frankly, I don't think you'll ever run into a hyperbolic function. I know that I, as a physicist, have never run into a hyperbolic function except in the math class. So I think it's pretty straightforward to say, let's just skip these. But in case you ever need to know it, just like now, except for the fact they look like they have names like the trig functions, they're not really related to trig functions at all, except for how they operate. Derivative of a sine is cosine. Derivative of a hyperbolic sine is hyperbolic cosine. Derivative of a cosine is negative sine, but the derivative of a hyperbolic cosine is positive sine. So these two go back and forth pretty straightforwardly, okay? Now, they haven't defined for you what a hyperbolic function is. Well, they did in the book. Let me put it down for you. And that's one of the reasons I don't even like messing with them, is because of this. The hyperbolic sine of x is simply defined to be e to the x minus e to the minus x over 2. Hyperbolic cosine of x is e to the x plus e to the minus x over 2. Okay? And frankly, I'd just as soon take derivatives of the exponential functions as I would trying to memorize the hyperbolics. Because exponentials are so easy to take derivatives of, why introduce another function and then have to memorize its formulas? Just take the derivative of the exponential functions and you've got it, okay? And these are what they are, and if you find that easier, use it, okay? And then you can get into your, well, here is your derivatives of the hyperbolic and trigonometric functions, written side by side. The other two, I've already told you what sines and cosine and hyperbolic cosine and hyperbolic cosine is. But you see, by the definition, there's nothing similar to it except how they do. Derivative of sine is secant squared, derivative of tangent is secant squared, derivative of hyperbolic tangent is hyperbolic secant squared. So you see, for the first three, sine, cosine, and tangent hyperbolics, they're all positive. Whereas before, it was plus minus plus, okay? Then hyperbolic cotangent, whatever that is minus hyperbolic cosecant squared, just like before. Derivative of hyperbolic secant, well, secant tangent is minus hyperbolic secant hyperbolic tangent. And derivative of hyperbolic of cosecant is minus cosecant cotangent, is hyperbolic is minus cosecant squared. Hyperbolic cosecant times hyperbolic cotangent. And frankly, if you probably aren't going to use hyperbolic sines and cosines, you sure are going to have these, okay, in my mind. But here they are. If you want to remember them, they're not hard to remember, but in my mind, why do it? I actually read a quote from Albert Einstein. Some reporter or somebody was talking with him and mentioned something about the speed of sound. And he said, well, whatever that is. And they said, you, Albert Einstein, don't know what the speed of sound is? And he said, it's a number I can look up. I don't commit it to memory. So he said, what's the point? I can always look it up if I ever need to know it. So why waste my time memorizing it? To me, same thing here. I don't know when I'm ever going to use it, but if I need them, I can look them up. I shouldn't say it that way, but to me, that's what we do with those. Okay. Now, so you got your hyperbolics and your derivatives of hyperbolics. I'm not going to test you on those. Guess what we do next? We take the inverse of these hyperbolic functions. Okay? Now, I guess it would have been helpful if I had drawn the graphs of the hyperbolic sine and hyperbolic cosine. If I had, well, I'll even show the hyperbolic sine. There's your hyperbolic cosine, like that. Can you do an inverse of that? Not if you include the negative part. So remember, inverse function has to be, to take an inverse, you have to be a one-to-one function. So it doesn't work over here, so don't even mess with it. Just take it here. There's the inverse hyperbolic cosine. Okay. Looks a lot like a hyperbola. It's not. I mean, a parabola. It's not, but it looks a lot like it. Okay. And then here's your hyperbolic secant. Now, the only thing that I can gather from this is the reciprocal of that. Okay? 1 is 1, and as this gets larger, this gets smaller. Okay? It just keeps on going like that. Well, then, again, you can't take the derivative of the negative. I mean, you can't do an inverse of the whole function, so just take the front half, and this is what it looks like. Not a very interesting looking function. When would you ever need it? I don't know. I can't even imagine needing anything like that, but if you need it, look it up. So here are the inverse hyperbolic functions and their derivatives. Is it worthwhile memorizing? Not in my book, but if you like memorizing things and you find it helpful and you might ever need it, go for it. Okay? Your inverse hyperbolic sine is basically defined for all x, not just a portion of it. Okay? I wish they had shown a graph of it. I can't believe they didn't do a graph of hyperbolic sine, but they did. Okay? That would be one that would be worth seeing as a graph. But its inverse is this. Derivative of this inverse is that. Now, that doesn't quite look like it is for inverse sine. That's 1 over the square root of 1 minus x squared. Okay? So, again, they're getting further and further apart. Who wants to remember how to do all the signs? Inverse hyperbolic cosine x is only defined for x greater than or equal to 1. If you remember, the inverse inverse hyperbolic cosine was like this, starting at 1 here, so the inverse is going to be starting at 1 here and going out. So you flip the thing. So that's why that exists, and its derivative is 1 sine off from that one, but not where I would expect it to be. Inverse hyperbolic tangent is define that. The derivative of that is 1 over 1 minus x squared, whereas for tangent it would be 1 x squared plus 1. Hyperbolic cotangent, whatever that is, its derivative is the same as
inverse derivative of inverse hyperbolic tangent. Hyperbolic secant is only defined from 0 to 1, including 1 but not including 0. And if you go back to the graph of that, you'll see why. It approaches 0 but never gets there, but it does go down to 1 and stops. So that's why it's only defined in that range, and its derivative is that, which, if you remember what the derivative of the secant was, I believe it's an absolute value x here, and x squared minus 1 over the radical there. They're sort of similar, but enough different to give you problems. An inverse hyperbolic cosecant, is good everywhere except where x equals 0. They haven't shown you the graph of that one. And when you take the derivative of that, it would be a minus here, and notice that only these two have minus signs on them. So it's a minus here, absolute value here, and reverse the order here, but change the sign as well. So I got here. Is it worth memorizing? I don't think so. And I probably talked too much about them. I'm not even wanting to do any problems unless you want to do any. You're not going to be responsible for them, so let them go. Okay. They do show one more graph, and this is the graph of the inverse hyperbolic tangent. That's the blue here, and you see that's why it's only between minus 1 and 1. I didn't notice that before. I didn't point it out anyway. Yeah, absolute value of x is less than 1. Okay, never approaching that. And you know, it almost kind of, in a little way, looks like a tangent curve. It goes through 0, it goes up there and down here, but it never repeats. It only stays in between that. Its limits are plus or minus 1, not minus I has to pi have. So everything else falls apart there. The hyperbolic cotangent, the inverse hyperbolic cotangent, notice it's not even defined where hyperbolic tangent is, and I didn't even notice that either. Let's see. Yeah, they just said the absolute value of x is greater than 1. So yeah, define down here, define over there, like that. Looks nothing like a cotangent function. So I don't know. But those two functions have what they call disjoint domains. They have nothing in common. Absolutely nothing. Okay? That means that's where the term disjoint comes from. And that's it for section 3.9. Homework, okay. Let's back up here. You want to do the preliminary questions? Yeah or nay? Second? I can't hear. We'll only do those that we're going to do. Like, I'll leave off any hyperbolics, but they don't have, well, wait. There is something. But let's take a look at them. Number 1. Goodness gracious. Pretty tight old windows, aren't they? Okay. What is the slope of the tangent line to y is equal to 4 to the x? We want the slope of the tangent line at x equals 0. The slope of the tangent line of that curve at x equals 0. Okay? Well, if you remember the formula for it, that would be fine. If you don't, why don't we do the same thing we just did? Let's take the log of it. The log of y is equal to x times the log of 4, right? Then take the derivative of that, and you have y prime over y is equal to log 4, right? Because that's the coefficient of x, okay? So your y prime is equal to log 4 times 4 to the x, okay? Now, maybe it would be better to say 4 to the x times log 4. I don't know which would be better. When x is equal to 0, what is the slope of that? What is 4 to the 0? 1. So y prime at x equals 0 is equal to log 4. Okay? So that's all we wanted. What is the slope of the tangent line of that at x equals 0? Now, they may have given you another formula before, but why not just use the one we've been using repeatedly, and that would be this one. Okay, let's see what we get. 3.9 preliminary question, log 4. Good deal. See it? Okay. Number 2. What is the rate of change of y is equal to log x at x equal 10? Well, what is the rate of change? If you ever see rate of change or rate of anything, think derivative. Okay? So what we do is dy dx at x equal 10 would be 1 over x. Derivative of log is 1 over x. At x equal 10, this would be 1/10. Right? You see it? Rate of change means how is y changing with x? Okay? And derivative of log x is 1 over x. Evaluate that, x equal 10, that would be 1/10. So it's changing really slowly by the time you get out to 10, and sure enough, 1/10. All right. What is b greater than 0? What is b is greater than 0 if the tangent line, what is the value of b, the positive value of b, 1 greater than 0, if the tangent line to y is equal to b to the x at x equals 0 has a slope of 2? That is really a weirdly worded question. So I think we'll start with a clean page on that. Okay? What is b, positive b, if the tangent line to y is equal to b to the x, the tangent line to that at x equals 0 has a slope of 2. What does that mean? That means y prime at x equals 0 is equal to 2. That's what it means. Okay? Well, what is your y prime? Again, not a bad idea to do a log. Log of y is equal to x log b, right? Take a log of both sides and do your thing. Take a derivative of this, and that will give you y prime over y is equal to x log b. And then y prime is equal to y times x times the log of b. Okay? So then your y prime at x equals 0 would be 0, right? That doesn't seem right. No, wait. No. Where did I get the x equals 0? Let me back off of here for a moment. We want this to be 2. We want that y prime at x equals 0 to be 2. But x is not defined. I mean, the function is not defined at x equals 0. Wait a minute. When x is equal to, let's back off here for a moment. When x is equal to 0, y is equal to b to the 0 is 1. Okay, y is equal to 1. So what's y? Can y prime be 2 then? I don't think so. What is b, a b greater than 0, if the tangent line 2, y is equal to b to the x, at x equals 0, has a slope of 2? When x is equal to 0, y is equal to 1. Okay? I'm not seeing what they're asking for here. Let's see if it'll make any sense. Number 3, they say, is e squared. Okay. They're saying if y is equal to e to the 2x, y prime would be 2e to the 2x. Right? And when x is equal to 0, the y prime would be 2. Yeah, that's right. I can see that their answer is correct, but I don't see how they got to it. What's that? What you say?
They use e to the x instead of natural log.
That's it.
They use e to the x instead of natural log.
No, they say what would be the b for that all this stuff to be true, and their answer was e squared. So I said, well, let's plug in e squared there and see if it works. And sure enough, it does work. But now I'm trying to see how they got to that. okay? And the y prime
I don't see how they got there. I see their answers right, but I don't see how they got there. There's something about the question that's really bizarre. Because it says, what is b, what positive value of b, if the tangent line to y is equal to b to the x equals 0 has a slope of 2.
Well, when x is equal to 0, y is equal to 1, okay? Okay, got that y is equal to 1, but what would it be its derivative have to be 2 then? If y is equal to 1 and it's 1, I really don't see how you could get
I don't think it's worth wasting any more time over it. Let's see if the next one makes any more sense. Okay. 4. What is b if log base b of x prime is equal to 1 over 3x? What is the b got to be? What is b if log base b of x prime is equal to 1 over 3x? Well, I know what they want you to do is okay, I think I see what they wanted you to do on 3 also. Let's go back to 3 quickly. What is b if the tangent line to y is equal to b to the x at x equals 0 has a slope of 2? Y prime is equal to 2. Here's what they wanted you to do. They wanted you to use the function at the very top in the summary. D by dx of b to the x is equal to log b, b to the x. Okay? So y prime is equal to log b times b to the x. Okay? We weren't far off from that before. Okay? And we want that equal to 2. At x equals 0, okay? At x equals 0, this one goes to 1. So that says log b is equal to 2. Then take the exponential of both sides, and you get b is equal to e squared. That's how they got it. Okay? So I shouldn't have done what I did. I should have gone back to the original form. And that gives it to you. So that's how they got that. Now let's look at this one. Well, what they're saying here was the derivative of log base b of x. Okay? Well, they give this to you. At the top of, on the summary,
they say this is 1 over ln b times x. Okay? And that's equal to 1 over 3x. Well then, from this, for those two to be equal, that says ln b is equal to 3. And if that's true, exponentiate both sides, b is equal to e cubed. So that's what they wanted you to do, that one. And that's pretty sure, yeah, that's b is equal to e cubed. All right, number 5. This is a hyperbolic. I'm not even going to mess with it. Okay. So let's move on. Homework exercises here. Do any of the odds 1 through 19. Do either 21 or 23 or both. Do any of the odds 25 to 35. Do any of the odds 37 to 43. Either or any of the odds 45 to 49, and any of the odds 51 to 73. Do either 75 or 77 or, well, wait, back off, wait a minute. Let's go back to the beginning. Any of the odds 1 through 19. That one I got right. Either 21 or 23, fine, or both. Any of the odds 25 through 35, that's fine. And then any of the odds 37 to 43, that's fine. Any of the odds 45 to 49, that's fine. Stop there. The rest of those are hyperbolic. I wouldn't worry with any of the rest of those. If you're interested, go for it, okay? If not, don't sweat it. Okay, I do want to point out something to you. Question number 81 mentions an equation called the logistic equation, okay? Which is, they show that this one function here, which involves a hyperbolic tangent, solves the logistic equation. Okay. The only reason I mention anything here is you do run into logistic equations if that's something that you're interested in. You said you're in biomedical science. The logistic equation is one that describes diseases. You know, it's sort of like a big figure S kind of, okay? A population that has not been exposed basically is going to have zero disease, okay? But then once this exposure happens, depending on how virulent and other things, then the slope of this depends on something, but it goes up and increases pretty rapidly until almost everybody's been infected, then it levels off again. That curve describes a logistic equation, okay? So if you think you may run into that, that may be one that you might want to do as a paper topic. I'm not saying you'll run into it, but it has possibilities. The next one talks about the Poisson-Boltzmann equation, which again has hyperbolics in it, which I'm beginning to be a little embarrassed because, but you see, every time I've ever needed these, they've been expressed in terms of exponentials, not in hyperbolics. So if you want to write on who Poisson was or who Boltzmann was, those are two good paper topics. Or how they came up with this equation, that's a good paper topic. I thought I saw something else that might be. Oh, they written in question 80, earthquake of Richter magnitude M, okay? And that involves a log equation, okay? So that doesn't have any hyperbolic to it at all, But if you want to write on who Richter was or how he came up with this, thing, that would be a potential, okay? And then there's a Palermo Technical Impact Scale. I've never heard of it. If it's something you're interested in, go for it. All right. Now, it seems like before we've skipped this section. I hate skipping this section, 310, because it's a really, really, I find fun type problems to do. But we really need to get on to the next chapter, applications of the derivative. And let me see if I have the test. I know I have the test made up, but I don't know if I have copies of it. Well, I say I know I have it made up. I can't lay my fingers on it. There's your test 1. What's that? Yeah, should be in Blackboard too, but if you want to see yours, since you're the only one in here, I will let you look at it while I leave back on my otherwise what's that? Yeah. Okay. That's test 1. There's test 1. Chapter 2 test. That's what test 1 was. Here's test 2. Let's see. Do I have? No, I don't. I can make you a copy of this right now if you'd like to take it, or give it to you Wednesday, either one. Okay. I wish I had already made copies. I thought I had, but in fact, I put my yellow sticky on it, but never filled it out. So evidently, I didn't get that done. Just make sure. No. Okay. Okay, you want to do that then? I will do that right at the end of class, and we'll walk out with you. All right. And let's see. End of class. We still got plenty of time. Let's move on to Chapter 4 then. And I think Chapter 4 is a little bit shorter chapter. Almost had to be. That last one was 10 sections. I don't know though. Yeah. I think this is only, goodness gracious. Yeah. It's only 8 sections, but we aren't going to do all of them. Okay. Actually, this shows 9, but I think we'll only, this is the old thing of the book. All right. Now, the new edition of the book has a different beginning from this one. This is talking about functions are one of the most important tools for analyzing phenomena. Biologists have studied the antler weight of male red deer as a function of age. Sounds pretty interesting. Yeah, I don't know. You're in biological sciences, so maybe that would be of interest. What's that? Yeah, we'll have bigger and bigger antlers, right? Right, yeah. Yeah, they get too old to hold them up. In your book, though, the new edition, sun tracking mirrors known as heliostats, and this happens to be in Spain, use the principle of least distance, which again is a function of a derivative. So both of these, I don't know, they love to do these little things, but they don't do really anything with them. So let's move on. Now, if you think back to our definition of what a derivative is, df dx basically, right? How much is f changing with a little bit of change to x? Well, if you think about that, the amount of the f is changing is basically your numerator, and your denominator would be your delta x, because that's what the x is changing. From a plus delta x to a, that's the delta x. So your delta f is just that difference in your function, okay, between f of a and a little bit past f of a. How much is that changing? Is it going up slightly, going down slightly, hardly changing at all? What is that delta f, okay? And this they're talking about linear approximations and application. If that delta x is small, that linear approximation is usually pretty good, okay? And here is the at least the first part of what you have in your book as this linear approximation of delta f. In the old edition, they didn't have as much as you did, okay? So here's what they've got. The delta f, the change of f, is approximately equal to the derivative times f of x, times your delta x. Because if you think about it, df dx that's what that is. And if rather than d by dx, you have delta f by delta x, multiply the delta x. If this is small, then multiplying the derivative of the function times that small delta x gives you how much your f has changed, okay? And what is your delta f? That is that difference quotient that we had before, the numerator part of the difference quotient. F of a plus delta x minus f of a. Now this is true if f is differentiable at x equal a and the delta x is pretty small. That's not a bad approximation. And you might say, so what? Okay? Now, the one other thing that's added in your text that's not in this one, and let me just make sure, no, it's not, okay, is this. Taking one more step from this one, your f of x, f of a plus delta x minus f of a, okay? That's your delta f. That's what this says. That's your delta f, okay? And that's approximately, I'm sorry. Not what I wanted to go with this. Okay. Let's combine these two, okay? The delta f is approximately, why is my pen not here? Okay, there we go. The delta f is approximately f prime times delta x. That basically comes from df dx, that's the same as f prime of x, right? Okay, evaluate at a, make it at a. Okay, well, change this to delta f over delta x is equal to f prime of a, and then multiply both sides by delta f, x, okay? And it wipes this out. So that's where you get this part. That is approximately equal to your derivative at a times your incremental part of x, okay? But what is this? This delta f is f of a plus x, a plus delta x minus f of a. Okay? Well, if you wanted to isolate this, f of a plus delta x, that would be f of a plus f prime of a delta x. Okay. That's what your book adds that this doesn't. This is approximately equal to, not exactly equal to. Now, I don't know if this looks like anything familiar to you. But you know they're saying a linear approximation. If you think about your equation for a straight line, you have several. Remember your point-slope formula? Your slope-intercept formula. Well, your point-slope formula would be y minus y1 is equal to slope times x minus x1. That's your delta x. So if you add your y1 to both sides, that gives you this. That's a linear approximation. Even if this function isn't linear, this gives you a linear approximation to it. Okay? Now, sometimes this is called the tangent line approximation, and here's where it comes from. Okay? And again, to me, this is a lot of talk about something that, frankly, I don't use a whole lot, but I guess in some areas you might. So, if this is your function, the blue line is your f of x, that is your function. But maybe that function's a really hairy thing and really messy and tough to deal with, and you want to know what is the value of that function just a little bit off from a. Well, if you use your linear approximation, that's going to be the tangent line approximation. Well, look at this. Between those values there, it's almost the same line, the same curve. Now you get out here and it gets way off, okay? Don't go out there. Keep your delta x small enough and you've got a really good approximation. That's what it's talking about. If your delta x is that big, you got some error there, okay? If you can live with that error, fine. But if not, take a smaller delta x, okay? So the delta f is the actual change of the graph of f of x, whereas your f prime of a times delta x, that's your change of your linear approximation of that. So that's your saying that this, the actual change of f is approximately equal to the linear off value of f. Okay. That's basically what they're saying. Now, let's do example 1. Let's see. This basically is what I was saying before. dy dx is f prime of a, right? dy dx is another way of saying f prime. So if you multiply dx by both sides, then you got dy is equal to f prime dx. Okay? At any given point, that is an equation. With deltas in here, it's an approximate. Okay. I don't know why they stuck it here, but I would have started with that. They didn't. Okay. Let's go back and do example 1. Okay. I think this is as good a place to put it as anything. Use a linear approximation to estimate 1 over 10.2 minus 1 over 10. What's the difference between those two values? Okay? It says use a linear approximation to estimate that. Okay? And then we'll actually estimate what 1 over 10.2 is. And then we'll actually figure it out. Okay. So what would you say your function is here? Your f of x here would be one over x, and we're evaluating it when x is equal to 10. Okay? So let's do our f prime of x. What would that be? Let's rewrite this as x to the minus 1. What would be your F prime then? Minus 1 over x squared. X to the minus 2, right? Is that right? Okay. Let me back off. Maybe skipping too many steps. Ah! The eraser doesn't pick up half the time. Okay. Let's do it this way. Okay. F of x is equal to x to the minus 1. F prime of x would be minus 1 x to the minus 2, right? Which would be minus 1 over x squared, right? Okay. Now, when x is equal to 10, f prime of 10 would then be negative 1 over 100, right? All right. Now, the change of f, which I think is what we're looking for, is approximately equal to this f prime of 10, which would be negative 1 over 100, times your delta x. Well, delta x here is 0.2, right? Between 10.2 and 10, right? That's your delta x. If x is 10, the delta x is that. So your delta f then is approximately minus 0.002. Okay? So what would be the difference of those two? Okay, we got that. Now, with your calculator, you got one handy? Oh, wait, okay. We didn't finish the problem. They then said find out, approximate what 1 over this would be. Okay. So this is your delta x. Okay. So we think this is approximately equal to minus 0.002. So let's add a tenth, which is 0.1, to both sides. And what would that give you? The 1 over 10.2 would then be approximately equal to positive 0.098, right? It's plus 1 minus, no. Yeah. Yeah, that would be approximately that. So this is the first part, the delta f, that difference would be this, and then from that we can get that the value should be close to that. So, with your calculator, do 1 over 10.2, or 10.2 to the minus 1, or however you do it on your calculator. Second? 9 what? 9.8, the same value? No, I mean, do the 1 over 10.2, just that, not minus the other. 1 over 10.2. Okay, they got in the book.
Okay. Okay, I'm guessing your calculator is set for it to round off too soon. Oh, that. Yeah. You see, 1.098034, blah, 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 blah. Okay, right. Okay, so it was very, very close. Okay. What did they say it was in the book? Oh, that's our approximate. Somewhere here, probably right here. Oh, no, that's here. Yeah. Yeah. And then when you add a tenth to that, it comes up awfully close. Okay. But yeah, that was the answer I was looking for. And it's very, very close to what we got. We got this one, they got with a 0.3, so it differs from what our estimate was, like 10 to the minus 4 or something like that. So not bad at all. Okay. Now, they talk here about differential notation. And again, your book, the new edition, expands on this pretty greatly. Okay? Well, actually, let's back up one. All right. In your book, in our book, the new edition, differential notation starts with this. Okay? dy is equal to f prime of a dx. Okay? And then the linear approximation says that the delta y is approximately equal to dx. Okay? The delta y is approximately equal to the dy. I'm sorry, I said dx. Okay? And again, I'm not really seeing, it seems like they're making much ado about not much. Okay? Let's see, this goes to 1040. Okay, so we got time. So let's do example 2. I'm trying to remember. I don't think that's the same thing, so let's see. Here's example 2. How much larger is the cube root of 8.1 than the cube root of 8? And we know what the cube root of 8 is. What? 2. Okay. So how much larger is the cube root of 8.1 than the cube root of 8? Okay. Well, again, what's our function? Y would here be equal to x to the 1/3, right? Where x is either 8 or 8.1. Well, what we do is y prime, or your dy, would then be what? 1/3 x to the minus 2/3. Perfect. 2/3. Okay, I wrote 2/2, which is a dumb thing to write. Okay. All right. So how much larger is the 8.1 times that? Well, our dy, or delta y, is approximately equal to f prime of x times your delta x. Okay? So how much is that? The change of your y is approximately equal to, and now this is where
x is equal to 8. Okay, so let's plug that in. Y prime, it'd be 1/3 times 8 to the minus 2/3 power times the delta x here. X is 8. Your delta x would be 0.1. 0.1. Okay, so this is approximately equal to 1/3 times, let's put this in the denominator, 1 over the cube root of 8 squared. Okay, now actually I prefer to do the square outside, so let me change that. You can write it either way. The cube root of 8 squared. Okay, and then that's times 0.1. Okay, so this is approximately equal to 1 over 3 times 1 over 2 squared times 0.1. Well, this is 1 over 12. 3 times 4 is 12 times 1 over 10. Okay, that's what that is. So this is approximately 1 over 120. Okay, so not a lot of difference. Okay, and what is 1 over 120? In the book they have, punch that in on your calculator and see if you get something pretty close to 0.00833333. 1 over 120. Yeah, 0.00833333. Okay. Okay. Now, if you punch that in on your calculator and do the cube root of 8.1, see what you get there. They say you get something pretty close. Well, actually, they're saying the same thing over again. Okay, sorry. Okay. Do we go to 1020 or 1040? Oh, 1110. Oh, my word, we did. Sorry about that. 1110. I have another class that starts on the hour, and it ends at 1:40. I got all crossed up. All right. We will pick up here with example 3, I think, or just before example 3. Okay, and let me give you just a few homework examples here, not too many. You can do any of the odds 1 through 5. Do number 7. I think you can do any of the odds, either 9 or 11. And I guess stop there. We'll pick up the rest of those later. Sorry about that. I didn't mean to go over.